This video will go over gradient descent. From our list of requirements to train logistic regression, we will focus on the algorithm for optimizing the objective function. We have a way of calculating loss, a measure of the distance between the true class and the predicted class. Now we need to reduce loss. To reduce loss, we need to alter theta. In the case of logistic regression, theta are the weights and bias. But in what way do we alter the weights and bias? Let's pretend we are working with only one feature, and therefore have only one weight. We can suppose that we have a graph of what the loss is at each possible weight value. Note, we cannot actually have a graph like this unless we calculate the loss for every weight value, which would take a really long time, especially as we add higher dimensionality. Let's say we are currently observing a training example and our weight is currently close to 0. To us viewing this graph, it is pretty clear that we would want to move the dot to the right. But why do we know that? We are using the slope. If the slope is negative, then that means that the loss will decrease if we move the weight to the right or in the positive direction. We usually calculate the slope using a derivative. You don't need to know how to calculate a derivative, but just know that the slope for cross-entropy loss is y hat minus y times x. That's all well and good for the case of having one weight value. But if we increase the number of features, which we will likely do, we can no longer calculate the slope using just a regular derivative. Instead, we have to calculate the gradient. The gradient is the derivative of a multivariable equation. It's a slope for when we have multiple weights. A gradient in this case is a vector that holds the partial derivative for the loss function with respect to each weight. Here is the equation for the gradient. It is a very big and scary equation, but if we break it down, we can see that it is a vector where each element is the activation function of the dot product of the weights and the feature vector plus the bias minus the true class y, all times the corresponding element of the feature vector. So for example, if we are calculating the first element of the gradient, we will use the first element of x. And if we are calculating the nth element of the gradient, we will use the nth element of x. But now the question is, how far in our decided direction do we want to move? If we move too far right, we could end up bouncing around in our loss curve. Likewise, if we don't move very far, we could be waiting for a very long time. We can influence how far we move on the curve, or in other words, how much to increase or decrease w, using what we call the learning rate. So the equation for finding a new weight at each step would be w at the next step is equal to w at the current step minus the learning rate times the derivative of the loss function with respect to w. We can plug in the gradient for the derivative, so the equation for finding the new weights vector at each step would be w at the next step is equal to w at the current step minus the learning rate times the gradient of the loss, which we outlined previously. And now we can use this equation to train our logistic regression model. These videos were inspired by Josh Starmer at StatQuest. Be sure to check them out.